So welcome back to the 7th lecture on supersymmetry. So I would like to start with a brief recap of where we got to last week. So we started analyzing the dynamics, the low energy dynamics of n=1 theories. And so remember, we saw what happens when we have pure supervier mills. In this case, using symmetries and the hypothesis of a mass gap, we wrote down an effective superpotential proportional to the strong scale, which predicted for us the existence of a non-vanishing gaugino condensate. Then we start discussing the super QCD. So for this theory, we can summarize in a table. So we have SU and C gauge group, and then we have various global symmetries for which it's convenient to write down a table. So we have a family of chiral fields Q that transforms in the fundamental of SU and F, and is a singlet under the other SU and F. And then we have a bunch of U1 global symmetries. And we need to fix this coefficient, these charges, by canceling the anomaly. So we have an anomaly for this baryonic symmetry that rotates in the same directions the Q and the Q tildes. So we also have the Q tildes. So for this theory, sorry, U1 we rotate in different directions, and for U1 baryonic, the Q and the Q tildes, and we can cancel with this assignment of charges the triangle where we have an insertion of the U1 big current and 2 gauge current. Then we have to check the assignments of our charges so that this other triangle is 0, and this led us to choose this U1R charge as NF minus NC over NF. Remember that under U1R also the gaugino is charged, so we also need to sum over the contribution of the gaugino to the anomaly. And then we have this axial U1, which we use to rotate. With this axial symmetry, we rotate both Q and Q tildes in the same direction, but in this case, the triangle diagram where we insert this U1A current and 2 gauge bosons is different from 0, so this symmetry is anomalous. But last week we learned that we should not really throw away the anomalous symmetries. We can, in a sense, revive them as pure symmetry and use them to get selection rules. So in the case for where NF is smaller than NC, we saw that there is a classical moduli space of vacua. Remember how we calculated the dimension of the moduli space of vacua. We count the solutions to the D terms. So there are no superpotential in this theory, so W is 0. So we only write down D terms, and D terms basically constrains the VEV that we can assign to the scalars that live in the Q and Q tilde superfields. So the total number of possible VEVs for the scalar living in the chiral multiplet is 2NF times NC, but we need to remove from this the number of complex scalars that through the Higgs mechanism that happen when we get this VEV, typically the gauge group is broken to NC minus NF. And because of this breaking, you have a Higgs mechanism, and in the process, a number of these complex scalars are broken. So when you count the dimension, we subtract away the number of broken generators. And equivalently, we can parameterize this moduli space by gauge invariant chiral fields, which are the mesons, which are color singlets. So we contract over the color indices, and we have SUNF times SUNF indices. So I can put also the mesons operators in this table that I'm drawing. So this is in the bifundamental of these two global symmetries, has charge 0 under the U1B, and has charge 2 NF minus NC over NF under U1R. So in this regime where NF is less than NC, so this is the picture that we have at the classical level, but we saw that at the quantum level, we can generate a superpotential, which is the Affledine-Seiberg superpotential. And we can cook up this superpotential with what we have. Basically, we have the strong scale. We have the gauge invariant, Lorentz invariant scalar that we can construct with the field strength. And then we have our light operator that parameterize the moduli space, the meson. We cook up a gauge invariant and an invariant under the two SUNF by taking the determinant. So I'm really using all this table. We use all the symmetry in this table to constrain this form, including, so we use symmetries plus spurious U1A. Remember, we said that this anomalous U1A symmetry is producing a shift of the theta angle, which we compensate by assigning a non-trivial transformation rule to the spurious field tau. Lambda to the b is basically e to the pi I tau, the holomorphic coupling. So we assign it a transformation under U1A, and this transformation restores this symmetry. So requiring you use this symmetry. So we require that WDS preserves all these symmetries, and including that we also want regular classical limit, lambda to 0 limit, and also we want to have positive powers of m to avoid non-local terms. And this for us basically constrained completely the form of the ADS superpotential, for which it is possible also to fix the constant. And it is given to, oops, three NF minus NC, the 1 over NC minus NF. So in particular, an interesting consequence of this superpotential is that, so we saw that it's consistent under various limits. So if we give VEV to some of the component of the meson matrix, this object consistently reduces to the superpotential, to the ADS superpotential of the theory that we have at low energy, where because of this VEV, the gauge group has been Higgs down. And in particular, if we give VEV to all the flavors, so it means that we no longer have any massless mode left over, because when we undergo Higgs mechanism, we end up with pure SUN C minus NF superamines. So we reduce to the superpotential for the superamines theory that we discussed initially, and in particular this was a check of our assumption of mass gap, because indeed we no longer have massless modes, and we have a non-vanishing constant, which now is fixed to be n. So the fact of the appearance at the quantum level of this ADS superpotential is that it generates a potential, of course, which has this runaway form. It means that the supersymmetric vacuum, remember, supersymmetric vacuum has to be at V equal to 0, runs at infinity. So this is the runaway behavior. So it means that basically the theory has no ground state. These mesons cannot take VEV then, and the VEVs, which used to parameterize the moduli space, I mean, this fact is telling us that the moduli space, which was huge, right? Classically, we calculated here the dimension of this moduli space, now is completely lifted at the quantum level. Then we discuss what happens when we have an F bigger than an C. Here we discussed the work by Seiberg. So the moduli space is parameterized by mesons, baryons, subject to various relations. And the first thing that we noticed is that there is a conformal window. So we can analyze the phases of this theory of the super QCD as we vary an F. So obviously there is an interesting point when an F is equal to 3nc, because at this point the beta function vanishes. So when an F is bigger than nc, than 3nc, we enter in a region which is the region of infrared free theories. So there are theories that the infrared, they become trivial with positive beta function, whereas when we are below, the beta function is negative. So we are talking about asymptotically free theories. We argue, however, that there is a window that is between 3nc and 3 over 2 nc, where we have this conformal window where we have a fixed point, a Banzas fixed point, which is an infrared attractive. So as we go to low energies, the coupling is attracted to these fixed point values. So you see, in this case, the coupling is not running indefinitely and becoming stronger and stronger as I go to low energy, but eventually it gets stuck. And then in this region, we have scale invariance, which is in fact full conformal and in fact super conformal symmetries. And we quoted only two facts about n equal 1 super conformal field theories. In this case, remember that they are charges part of the superconformal algebra, and it is a generator, and there is a relation between the eigenvalue of the dilaton and of their charge, which implies that the dimension, which is the eigenvalue of the dilaton, has to be bigger or equal to the R charge, to the modulus of their charge. And for chiral, and in particular for chiral operator, then we have the delta is exactly equal to 3 over 2 R. And in particular, these allow us to calculate the dimension of the mesons, which is then 3 over 2 their charge of the mesons, which is twice then their charge of the quarks, which is NF minus NC over 2. Sorry, too many souls. No, it's okay. So there is another fact that is true in every CFT, which is the existence of unitarity bound. So unitarity requires that scalars must have a dimension bigger or equal than d minus 2 over 2, which is the dimension of a free scalar, which in d equal 4, it's 1. So this implies, these two arguments combined, implies that the dimension of the meson has to be bigger or equal than 1. When the dimension of the meson is 1, which happens precisely when NF is equal to 3 over 2 and C, they are free. So we think that something is going on when you go below this value of NF. We must enter into a different phase where we no longer have a conformal field theory. So we enter in a region where we have strong coupling and confinement, and this region extends up to NC. We need to discuss this, and we still need to finish this discussion. Then remember, starting from NC, then we have the ADS superpotential that we just discussed until we get to super Yang-Mills, which has instead the strict confinement, the Gaugino condensate. There was the second proposal put forward by Seiberg, which is the existence of a duality, which is proposed for an F bigger than C plus 1. So in this regime, the proposal is that the original theory that we call electric, which is SU and C with NF Qs and NF Q tildes and no superpotential, is dual to another theory, which is we call magnetic super QCD. Now the gauge group is SUNF minus NC. We call this NC tilde, and it has still NF chiral Qs and NF chirals Q tilde. But now there is also a set of singlets, XIJs, which transforming the bifundamental of SUNF times SUNF. But they are singlet under gauge, and they enter the superpotential with a cubic coupling with the dual quarks Q and Q tilde. So the idea is that in the original theory, we saw that the moduli space is parameterized by the quarks and then the baryons. I'm not writing down the indices of the baryons. And in the dual theory, we don't have the mesons, obviously, because if we write down the F terms for the field Xij, we just get Qi Q tilde J, which would be the dual meson matrix set to 0, but then the moduli space can be parameterized by the singlets Xij and the baryons constructed with the dual quarks. So last week we discussed how one can establish a map from between these operators, meaning that we can check that they transform under the same representations of the global symmetry groups. So they have the same charges under the U1s. So the map goes that the mesons are mapped to the singlets Xijs, And then there is a relations between baryons by appropriately contracting the indices. And something that we will not do, but one can check that they also, this, as I said, in the original Super QCD, the moduli space is indeed parameterized by mesons and baryons, but they do satisfy relations, so they are not all independent. And one can check that also in the dual theories, these sets of operators satisfies relations. So you can map operators and relations. I'm referring to these relations that were related to the rank of the matrices, these classical relations. So the claim by Seiberg is that if you take the magnetic super QCD and you turn off the superpotential, but you keep the extra fields Xij's, so this theory too has a conformal window. And so for this theory, there is the interesting points is 3/2 NC, which determines the points where the beta function is 0. So now you will have a region where beta is positive. So you have this infrared free theory. And then you have this region, which is the confining region, so the asymptotically free region where beta is negative. In between, there is the conformal window. And this value, where NF is equal to 3NC, is where the dual mesons become free. So in this window, we also have a fixed point G star. And the claim is that if you study the theory at this point, you can show that the operator X QQ tilde, which is precisely the superpotential that we introduced in the dual theory, is relevant. And when you turn it on, so it's relevant and you want to turn it on. And so this deformation drives G star tilde, which is the fixed point that you have in the dual theory, to G star. So the claim is that if you sit in the conformal window, so NF is between 3NC and 3/2 NC, then the two theories, the electric super QCD and the magnetic super QCD, flow exactly to the same fixed point. And you have a superconformal field theory. So what happens then, so we, in this region, which we still have to discuss, which is NC plus 1 bigger than NF, smaller than 3NC. So in this region, the electric theory has a beta function negative, and it is confining. So this is a theory which is very hard to study. And we know that mesons become free. So we need to understand what's going on here, and it's difficult, obviously, because the coupling is running. Since we think we left the conformal window, the coupling is running and running and becoming stronger and stronger. So here is really strongly coupled reason, and it's very hard. But if the duality is true, then in this region, the magnetic theory has beta function positive. So in the infrared, this theory is stupid, it's very simple. So we have that the coupling of the magnetic theory is going to 0. This means that we have an infrared free theory. And in fact, also, if we had turned on lambda coupling for in front of W, so imagine we write the superpotentials lambda x q q tilde. So in the infrared, also this coupling is going to 0. So if the superpotential is going to 0, it means that now we're talking about the magnetic theory. So the field, the fields Xij's, the singlets, are free. So if they are free, it means also that the superpotential is not being not there, is not fixing anymore. There is an extra U1 symmetry that rotates these fields. So we have an extra U1 symmetry in the game. And this extra U1 symmetry that, let me call it U1X, that is acting on these fields which are now free, can combine with the R-symmetry. So remember that I told you that if you have an R-symmetry, this is not unique. If you have an R-symmetry and another U1 symmetry in your theory, you can take linear combination. So this here is a linear combination that I'm doing between R, which is the generator of the original R-symmetry, and X, which is the generator of this new extra U1 symmetry that I gain because now I have an extra symmetry that rotates the Xij fields, and I can make a linear combination with some coefficient alpha. I need this because then it has to be true that since the fields Xij's are free, then we must have that the dimension of R, so let me call actually this R prime, the dimension, the R charge, if these fields are free, then they must have dimension 1 because they are free. And moreover, we know the relation between R charge and dimension, they must have R charge 2/3. So I need this combination with this extra generator to guarantee that this condition is satisfied for generic values of NF below 3/2 NC. So precisely at NF equal to 3/2 NC, the R charge is 2/3. Then when I go below, I need always to saturate this condition because these fields are free, and this I can do thanks to the combination with the extra U1 symmetry. But okay, what is important for us is that in the dual theory, as we said, the coupling G magnetic is going to 0. So this theory, it's trivial, and it is dual to a very complicated theory. Which is the electric super QCD, which has a coupling G electric, which is going to infinity. So we learn by looking at the dual theory that in this region, in the confined phase, is better described by free dual quarks. So if we manage, so this is always the dream that we have when we have a strongly interacting theory. The paradigm is that maybe you can find a better set of degrees of freedom in which your complicated strongly coupled description is weakly coupled. So this is, for example, the case of holography, and you will learn about this starting from this week. In this case, we see that the better description of the very complicated, strongly interacting QCD, where we expect to find quarks bounded in mesons and baryons, it's better described by free dual quarks. So these sets of fields that are elementary fields of the dual super QCD, it's the correct sets of the degrees of freedom to have a weakly coupled description of the strongly interacting phase. And so we need to discuss then what happens if we go below NC+1. So now the dual gauge group NC tilde becomes 0. So clearly here the Seiberg description, the Seiberg duality doesn't work. In fact, we also know that for an F smaller than NC, we have, well, strictly smaller than NC, we have the ADS dual superpotential. So in fact, we only need to discuss two cases, which is an F equal to NC+1 and an F equal to NC. So we will have a quick look at these two cases, and then we will just make a few remarks more on the checks for the duality, and we'll move on. So let's start discussing the first case, NF equal to NC. So here you can check that if you calculate the charges of the quarks, remember our formula, their charges, this is NF minus NC over NF, and this is 0. And so it's basically, you cannot, if you try to extend the DS description, you cannot hook up an R charge 2 object, which would be your double effective. So what we know about this theory at the classical level, remember we discussed that we have the mesons and then we have the baryons, but in the case in which NF is equal to NC, the baryons, remember the formula for the baryons where you use two sets of the antisymmetric tensors, they are basically the determinant of the matrix Q, which is now a square matrix. You have the gauge indices and the flavor indices, they both run up to NC. So when you contract with two sets of the epsilons, you get the determinant. And then we have this classical relation, which is the determinant of the meson matrix, which is obviously the product of the determinant of the quarks matrices, is just equal to B times B tilde. This was a classical relation. So we can wonder whether this classical relation gets modified quantum mechanically, and we can check. I mean, it's natural to write down a modification. So we can try to see if on the dimensional grounds you can modify this equation. And there is a pretty obvious thing that you can do. If you just look at dimensions, you can just use the strongly coupled scale raised to the suitable power, which is NC. So this is dimensionally allowed. The symmetries are allowed. So it is allowed. The question is that, is it true that it gets modified? So basically, again, the question boils down to check whether this constant is 0 or non-zero. By the way, notice that lambda to the 2nc is nothing but e to the 2 pi nc. In this case, 2nc is just b1, okay, the one loop coefficient. So this is 2 pi I tau, and so this is nothing but the instant on action. So this is a clear instant on effect that may appear to deform the moduli space. So we said that we cannot really write a superpotential, but what we can do something quite different. We can write down a superpotential with an auxiliary fields that enforces this constraint. So can construct a superpotential W with a new field, which is lambda, which is a Lagrange multiplier, which multiplies precisely the constraint that I am guessing. So when I use the equation of motion for the Lagrange multiplier, I get this deformation of the classical moduli space. You can ask me whether this thing makes any sense, and what are the sanity checks that you can do in these cases. So we are, in a sense, thinking that this is the superpotential that we should write down when NF is equal precisely to NC. But we know that if we just lose one flavor, we know where we should go. We should go to the ADS superpotential. So there is a sanity check. So it can be checked that if you deform W by a mass deformation, so you turn on a mass term for the bottom component of the Meson matrix. So you just give a mass to the last flavor. So this is just Q and C, Q tilde and C. Now you integrate out one flavor, you get SUNC, and NF equal now to NC minus 1. So our W must match into the ADS superpotential. And you can check that this nicely happens. And you can also fix the constant that we wrote here to 1, which is obviously non-zero. So this idea of introducing this Lagrange multiplier, which then is set to 0 by the equation of motions when you do this integrating out one flavor. So you nicely recover the ADS superpotential. So this seems to be correct. So what does it mean then for our moduli space, the fact that it's deformed? Okay, so remember that the classical moduli space, which is described by baryon and meson subject to this equation, it's basically a singular moduli space. And there is a singularity, and this singularity it's obviously the singularity that is due to the fact that at this point where we don't get waves to baryons and mesons, the gauge group is not fully broken. Then you have a singularity due to massless gluons. In the quantum case, this equation, you see, is deformed. So now we no longer have a singularity because we don't have a zero on the right-hand side. We get something that resolves the singularity. So now the moduli space is smooth and there are no singularity. And notice that at the quantum level, then when we use the equation of motion of the superpotential that we wrote, tell us that you can have well, you can have different types of well, you can just look at the form of the equations to conclude that you can have two types of branches. We have the so-called Meson branches, where the wave that you can give to the mesons are non-zero. And in the quantum case, this is always non-zero because you have the scale lambda. And the baryons, however, are not taking waves. And you can have instead a baryon branch, baryonic branch, where instead the mesons, they don't take a wave, but the baryons do. So clearly the first type of wave, where you turn on a wave for the mesons, has the effect of breaking the SUNF times SUNF global symmetry just to a single diagonal SUNF. So this pattern of breaking is similar to what you have in QCD, in ordinary QCD, where you have the so-called chiral symmetry breaking. Okay, you break the chiral symmetry that rotates of the two SU3, you preserve only one SU3. Whereas in the second baryonic branch, you obviously preserve this global symmetry and you break completely only the baryonic symmetry. So in this case, we have indeed confinement, but we have confinement associated to breaking of some of the global symmetries. So to use the analogy with QCD, we call it this a vacuum, sorry, a confinement with chiral symmetry breaking, although there can be different patterns of breaking. Instead, when an F is equal to NC plus 1, okay, so in this case, we have the baryons, they still carry an index going and from 1 to NC plus 1. And in this case, you can check using all the symmetries that you can cook up a superpotential, an effective superpotential, which has some, again, constant A prime, and then determinant of the Meson matrix, Bi, Mij, B tilde J. And here you need by dimension the strong scale. B in this case is 3 and C minus and C plus 1. So it's 2 and C minus 1. So this is allowed by dimensions. And you can check whether this guess makes sense in the same with the same trick. So you take this double effective and you do a mass deformation. So you turn on a mass for the NC plus 1 and C plus 1 component of the Meson matrix. And if you do so, you can check that you reproduce precisely the quantum deformation of the moduli space for the theory with SU and C and NF equal to NC. So you get, by consistency, you get the constraint that we discussed a moment ago. And on top of that, you check that, I mean, you are forced to fix this constant A prime equal to 1. So also in this case, a posteriori, you can convince yourself that the answers that you make with this for the effective superpotential make sense. So now, using this effective superpotential, you can write down the equation of motions. And this set of equation of motion are more or less as follows. So you have equation of motions for the baryons. And then you have the equation of motions for the mesons. So you have here you have the determinant of M. So when you differentiate respect to the component of Mij of Ij of the meson matrix, you get the minor Ij minus Bi B tilde J. Remember, the minor it's the determinant of the matrix from which you deleted the I and J row. Okay, so what are these equation of motion telling us is that now, I mean, the most important thing is that the origin M equal to 0, B equal to 0, and B tilde equal to 0, obviously we are talking about VEV, is not removed from the moduli space. As it happened in the previous case. In the previous case, the origin where we don't get any VEV was removed at the quantum level. So we went from a singular to a smooth moduli space at the quantum level. Whereas in this case, this point is not removed. And at this point where there is no VEVs, we don't break any global symmetry. So basically, the physics of these two cases, NF equal to NC and NF equal to NC plus 1, they are similar. So we have, in both cases, we have confinement, but no mass gap. In fact, in both cases, we still found massless object like mesons and baryons. And in both cases, we found a moduli space. So there is not lifted as in the NF less than NC case. So there is no runaway superpotential. This moduli space can be deformed respect to the classical one, or it can be, as in this case, just classical, because basically we got it from the set of equation of motions. And it can be that there is, or there isn't, chiral symmetry breaking. Where really, by chiral symmetry, we just mean whether we are breaking completely or not completely the global symmetries. And yes, then we know that if an F is less than an C, we just reviewed it, the ADS superpotential lifts the moduli space. And finally, we get to an F equal to 0, where we have superion mills with mass gap. And remember, in this case, we had isolated vacua. So there is no really a moduli space. There are isolated vacua, which are labeled by the phase by which the gaugino condensate is rotated. Right, so there is an important thing that I would like to mention, which is how you test, right, dualities, which is also an important tool that was used in the past and is used currently to conjecture a duality, which is the match of the anomalies. So when we had our quick recap on anomalies, I review for you the argument by Toft for the matching of the triangle diagrams involving only global symmetries. And so I would like to do some of these checks, and maybe the rest you can do yourself as an exercise. So we can do, for example, look at the triangle diagram where we insert two U1 R currents. So in this case, the coefficient that we need to look at is R, A, R, R, R. And this is just very simple, is the sum over all the fermions running the triangle I sum over their charge under U1R to the cube. So let's calculate these in the electric theory. So first of all, I have the Weil fermions that sit in Q and Q tilde. So how many of them I have? I have 2 NF times NC. Right, Q and Q tilde, they are chiral fields, and their Weil fermion sits into the fundamental of the gauge group and the fundamental of the global symmetry group SU and F. I have 2 of them, Q and Q tilde. Then I multiply by the R charge of Q minus 1 to the cube. Remember that the R charge of the fermion sitting in the multiplet is the R charge of the scalar, which is also the R charge of all the multiplet, minus 1, because theta carries R charge 1, okay? Then that's not the end of the story, because another fermion is the gaugino, and the gaugino is charged under U1R. So how many gauginos do we have? The gaugino is in the adjoint, so we have NC square minus 1 gauginos. And I multiply by the R charge of the gaugino, which is 1. So if you do your math, then you find 2 NF to the 4th divided by NC square plus NC square minus 1. Then we can calculate the same anomaly in the magnetic theory. So now again we have the contribution of the dual quarks. So we have 2 NF times NC tilde. NC tilde is NF minus NC. So here I will put the R charge of the dual quark, -1 cube. Now, we also have the singlets Xij's, which are in the bifundamental of SUNF times SUNF. So I have NF squares of the Xij's. So these are Xij's. And of course, I still have the gaugino. So I have NC tilde -1 times the R charge of the dual gaugino, which is always 1. So you can check that if you do all the simplifications, this luckily matches the anomaly of the electric theory. So we do one more, and then the rest you can do as an exercise. We can do a triangle diagram where we insert U and R at one vertex, and then we put two global SUNF, say left current. So we have two SUNFs. Now I'm calling one left and one right, but so I want to have SUNF, SUNF. So this is the triangle that we can say, we call it U1 R LL. And this is, so we can calculate it again for the electric theory. So how many fermions transform we have? So under the SUNF L, we only have the Q's, not the Q tildes, because the Q tildes are singlets under SUNF L, so they don't contribute. So they transform in the fundamental of the gauge group. So we have NC of them. Then I need to multiply by the Dinkin index of the fundamental. So this is the fundamental of SUNF left. And then I put the R charge of Q -1. Remember, this is the formula for this triangle where I have, it's basically the ABJ, it's like the ABJ anomalies, but now instead of using SUNC, I just focus on SUNF left, this global symmetry. And that's it, right? There is nothing else. The gaugino is not charged under SUNF left. So this gives me NC. T of the fundamental is just a half, and then I have minus NC over NF. So this is minus NC square divided by 2NF. And then you can do the same on the magnetic super QCD. So now you have, again, the contribution of the Q tilde quarks, sorry, of the small q quarks. Then you have the contribution of the singlets. So the singlets, now I have, they are in the fundamental of SUNF left and SUNF, let's call it right, the other one. So I have NF of them, T of the fundamental of SUNF left, and then I have R of X -1. And okay, I will not do all the simplifications, but you can check that this is NC squared minus 2NF. So as an exercise, you can check the other anomalies. So you can calculate, for example, SUNF left or right, but instead of putting U1R, you can put U1B. You can do U1 square B with U1R. You can do, for example, trivially U1B square. This is, sorry, cube. This is obviously, you will check in 2 seconds that you get 0. And then you can do 3 SUNF left current or 3 SU NF right currents. So you can do this exercise, and that was it's a very important tool to check dualities and even to conjecture dualities. And there is another standard technique that was used to make checks. In fact, we already used the idea of giving mass to some of the flavors to see that when we giving mass or giving VEV to the theories to see whether at low energy we get what is expected by consistency. So there is this consistency check that we can do. So we can say that in the electric theory, we give mass to a flavor. It means that we turn on a superpotential deformation on the electric theory, which is a mass term. So it's M Q NF Q tilde A NF. So it's a gauge singlet. I'm always contracting the gauge indices, and I'm focusing on the last flavor components. So I'm giving mass to this last flavor. And what happens when I go to low energy? At low energy, simply I lose one flavor. I integrate out one of the flavors. So we simply get a theory which has the same gauge group, S2 and C, but the number of flavor is now NF minus 1, and the superpotential now is 0. Okay, I just integrated out the flavor that got a mass. Now, what happens on the dual side when we turn on a mass in the electric side? So we need, remember, we established a map between operators. So this guy here is just the NF entry of the Meson matrix. And we know that the Meson is mapped into the singlets. So in the dual theory, I am turning on a deformation which contains just the component NF of the singlet matrix. Remember, this was just a particular component of the operator map that we established for the duality. So what is the effect of deforming the theory by the last component of the singlet matrix? Well, now we have in the dual theory, the total superpotential. Remember, we had Qi, Q tilde J, X, Ij. That was the superpotential we had originally in the magnetic super QCD. Now we have this deformation. So if I use, when we write down the equation of motions of the F terms for the component NF and F of the singlets matrix, this is telling me that QA and F, Q tilde A and F plus M, it's equal to 0. Okay, but this is what? This is just to say that this component is getting a non-zero VEV. It's a VEV. By now we know what happens when we turn on a VEV. We trigger some Higgs mechanism. So at low energy, we get SU NF minus NC minus 1 with one flavor left. Okay, so that's the effect of the Higgsing. I just Higgs down by 1 unit the gauge group because I gave VEV only to one flavor. The other equation of motions, so if I use the equation of motion for Q and F and Q tilde and F, what do we find? We find that X and F J contracted with Q tilde J is 0. And this is the same of X contracted with Qi. So as a matrix, the singlet matrix Xij is fixed to have a 0 column and a 0 row. So it here I have a matrix X prime Ij, which has only an F minus 1 by an F minus 1 entries. So this is a consistency relations because we have the following situation. So we have SU and C with an F, flavors, which is dual originally to SU and F minus and C and with an F flavors and W equal to X Q tilde. Then if I do here a mass deformation, we land on a theory which has just one flavor left. So I have SUNC with an F minus 1 flavors. We saw that, however, this mass deformation on the dual side is just some Higgsing. And the effect of the Higgsing is just to Higgs the theory to SU and C minus an F minus 1 with an F minus 1 flavors and W being X prime Q tilde. So X prime is the correct singlet matrix to enter in the superpotential for the theory with one less flavor. And here also in this bottom row, this diagram, I can establish, I mean, I can go horizontally by applying Seiberg duality. So that's precisely the correct dual magnetic gauge group predicted by the duality. So you see that the duality, it's behaves consistently under this operation, which is giving mass on one side, which corresponds to giving VEV on the dual side. And you can also do the reverse. Of course, if you can give a mass to the magnetic side, which corresponds to a VEV on the dual side. So before closing this chapter about N=1 theories, I just want to say something concerning the modern developments. So here we are in the 90s. Okay, so these games have been played throughout the 90s. And in fact, many dualities have been discovered, which are a generalization of Seiberg dualities for different gauge groups and also in like other dimensions. For example, in 3 dimensions, there is a list of dualities which are close relatives to Seiberg dualities in 4 dimensions. And the tools that were used through the 90s and the early 2000s were basically these ones that I just reviewed for you, mostly matching anomalies, trying to map the modular space and doing these tricks of consistency checks, giving masses, giving VEVs. But since say 2010, there has been a new tool, and this has become really now one of the standard tools to work on dualities. And this tool is the Superconformal Index. So I don't have time in this series of lectures to talk about this. I just want to mention that it exists. So this object is now the modern tool to study dualities. And is this supersymmetric index. And this object has basically two distinct definitions. So it was originally defined by two groups. So there is work by Kinney, Maldacena, Minwalla, and Raju, and then the work by Rommelsberger. So this is the work from 2005. And in this approach, the index is presented really as an index. That is, it's a trace with some refinements. Okay, so there are some -1 to the f, which is the Fermi number operator insertion and other insertion, but anyway, is a trace over the states of the theory quantized radially. So we are on S3 times R. Alternatively, this object can be defined as a partition function on S3 times S1 and can be calculated by localization. And the localization we have in mind here is basically the one, is the Witten localization, but in the version revamped by Pestun in 2007. So basically, an important step was done by Dolan and Osborne in 2008. They managed to rewrite this object so they really show that this index, as formulated as a trace over the states of the theory, can be rewritten as an integral of elliptic gamma functions. So it's a they show that these superconformal indices can be written as matrix integrals involving certain functions, which are these elliptic gamma functions. And interestingly, these integrals that they wrote turn out to be very well studied by certain mathematicians. So there was work by independent work mathematicians involved in these works were Spiridonov and Rines and others. And what these people were independently doing is really studying matrix integrals involving these elliptic gamma functions. And they proved tons and tons and tons of identities, integral identities for these functions. And why this work then became particularly relevant for the physics community? Well, in the context of dualities, the most important thing is that the index can be written in terms of the UV data of the theory. So if I give you a Lagrangian, you can write down the index. So if we have an infrared duality like the cyber duality that we just discussed, where we had electric super QCD and magnetic super QCD that are they have two different UV Lagrangian, but they flow to the same infrared fixed point, then it must be that I can write down the indices for these two UV Lagrangians. And well, sorry, the important statement here is that the index can be written in terms of the UV data of the theory, and it is an RG invariant. Okay, so you write it from the UV Lagrangian, and then that's it. So then it just won't vary as you move toward the infrared. So in the case in which you have an infrared duality like Seiberg duality, so if you have a duality where, say, theory A is dual to theory B, where dual, we mean that they flow to the same point in the infrared, then the check of the duality is basically saying that the index of theory A is equal to the index of theory B. So it's a math statement. You just need to check some identity that relates these two expressions. And amazingly, you know, these mathematicians have been proved for us the relevant identities to check most of the dualities that we knew, and many more identities were known to the mathematicians that had the effect of triggering the discovery of new dualities in physics. So there was really a lot of activities starting from 2011 and so on, from this series of observations. So there were early checks really of the cyber dualities, and then from then onward there is lots of activities in this direction. So I can point you just to a reference, is a review by, well, there is a chapter written by Rastelli and Razamat in the review on localization by Pestun Zabzin from 2016. So if you, well, the review contains also a nice introduction to technique of localization that you may want to look at. And in particular, there is this chapter by Rastelli and Razamat, where they go through the definition of the superconformal index and discuss various applications, including the application to the test of dualities. And this is a huge field, and we will not discuss this point further. So now the plan would be to move to theories with higher supersymmetry, mostly to n equal 2. So if you have questions on this part, you can ask questions now, later. Remember also that today we have the office hours. But if you have questions, of course, that's a good time now. Okay, so maybe you will ask all your questions later. So let me just transition into the next topic, but we need to kind of go back to the constructions of supersymmetric Lagrangian for theories with extended supersymmetries, because we have been focusing just on unequal one supersymmetry. So let me go back for a moment to the representation theory of the superconformal algebra. Remember that in the case of n equal 2, we have two sets of creation operator. So we are looking at massless representations here as usual. So we have two supercharges, so we could construct two sets of creation operators. Only two, remember, not four, because we have well, say two of the supercharges are represented trivially, so they are not there as generators. And then starting from helicity states with helicity 0, we constructed the so-called vector n equal 2 vector multiplet. Remember, so we start from helicity 0, and then we act with A dagger 1, A dagger 2, and both the supercharges. So in this way, and then we add the CPT conjugate. In this way, we constructed a state which has 4 fermionic, which are 2 Weyl fermions, and 4 bosonic states on shell. The 2 bosonic states corresponds to the 2 polarization of a vector and then a complex scalar. So in terms of in the n equal 1 language, it's like, so this is the n equal 2 vector multiplet. In terms of n equal 1 states, this is like the combination of a vector plus chiral multiplets. So we can just use this piece of information. We have already done the work for representing in terms of fields the superalgebra in n equal 1. So now we just know that we need to pair a vector and a chiral superfield, but we need to be consistent with the R-symmetry. So the idea is that we want to take the vector multiplet of n equal 2, of n equal 1. Remember, this has a Gay-Gino and a vector. Now I'm calling it a mu. We have been calling it v mu, but it doesn't really matter. And then we have a chiral multiplet. I'm writing them in this form just for convenience. So these two fields belong to the n equal 1 vector multiplet, and these two complex scalar and other Weyl fermion sit in a chiral n equal 1. So I'm writing them in this form because I want to highlight the action of the R-symmetry. So there is a SU2R symmetry. You can see in the representation we acted with the A dagger and A dagger 2 to create fermionic states. So there is the two fermions, they carry an SU2R index. So for this reason, basically we need to have the two fermions rotated by SU2R as a doublet. And of course, all the fields here, they are in the adjoint representation. because they belong to the same multiplet. So off shell here we are talking about of 8 fermionic plus 8 bosonic degrees of freedom. And the fermions will be doublets under SU2R symmetry, whereas all the other fields, so a mu, the scalars, and the auxiliary fields, D and F, they will be singlets under SU2R. So when I try to construct a Lagrangian, well, we know how to write a SUSY invariant Lagrangian, which respect n equal 1. Now, basically, to respect n equal to 2, I need to include together a vector and a chiral n equal 1 superfields and avoid spoiling the SU2R symmetry that rotates these two fermions, because basically it's the symmetry that rotates the two R charges. So this means that when I write a Lagrangian that needs to preserve SU2R, there are many things that I cannot do as I like. So I need to choose same normalization for kinetic terms of the fermion sitting in the chiral multiplet psi and for the gaugino. And basically, I cannot turn on a superpotential, because the superpotential will involve only phi, the chiral superfield, and then it will create an imbalance between the fermions psi and the gaugino. So you see, I don't have really much freedom. So the only thing that I can write down is the following. So this part we already discussed. It's the n equal 1 super Yang-Mills part. Good. And then I need to add the contribution of the chiral, which we know how to write in a supersymmetric gauge invariant fashion. And the point is that I cannot put an arbitrary normalization here. This has to be fixed so that I have SU2R symmetry preserved, which we can make sure that things work just checking how this thing looks in components. So let's do this exercise. So when I expand everything in components, so we have familiar kinetic terms. The theta angle. Notice I'm using the canonical normalization, so now the gauge coupling will sit as it should when in front of the interaction terms. So here I have the Yukawa couplings. So we, for the Yukawa couplings is really where we need to look at the SU2R invariance, okay? Because they can, the fermions are the one carrying SU2R indices. So first of all, remember that here all the fields, they are in the adjoint of the gauge group. So the gauginos, the various fermions, and the chiral. And also the auxiliary fields. Now let's look at this Yukawa coupling. So what do we mean when we write trace phi bar lambda psi? This is, we mean phi bar, say B lambda A, T A B C psi C. So we already discussed how indices go for the Yukawa in the n equal 1 case. The difference is now these generators are in the adjoint because every field is in the adjoint. So this is really F A B C is the total antisymmetric structure constant, which implies, and this will be important later, that if the gauge group is U1, there are no interactions. So in general, I mean, with the indices contracted in this way, you do preserve SU2R rotating the fermions. Moreover, there is another U1R, which is the one that we checked for the n equal 1 Lagrangian. And this you can check, for example, you remember we had an U1R, so if you look at the term, which is like, say, phi bar psi lambda, in terms of charges, so this has to preserve our symmetry must have our charge 2. So if I assign the same R charge to the gaugino, which is always 1, and to the other chiral, so that they are rotated by the other SU2R, this fixes the R charge of the scalar to be 2. And this is something that we need to keep in mind. So I can define also, on top of SU2R, I can define an assignment of U1 charges under another U1, which is another U1R symmetry. Okay, so, and then of course there are the usual consideration why phi has to go, sorry, in fact here I forgot phi. So why I have to go to have phi together with psi bar and lambda is really to define a consistent U1R. Obviously phi bar will have R charge -2. And so let's look at the equation of motions for the auxiliary fields. So the equation of motion for F will simply set to 0 all the auxiliary field in the chiral multiplet, whereas the D terms, the equations for motion for D, will tell us that D is equal to, you see, D appears here and here. So the equation of motion for the field dA will tell us that dA is equal to G commutator phi with bar phi component A. So when we plug this equation of motion back into the Lagrangian, we get the scalar potential which is simply G square, the trace of phi bar square. So the supersymmetric vacua which, as we know, they are the solution of zero energy, clearly corresponds to the waves of these scalar fields, compatible, okay, with the fact that V is zero. So I need to kill the commutator of phi with phi bar. So phi commuting with phi bar means that I can put phi in a, put the phi, and so it's a possible wave in a diagonal form with the condition that the eigenvalue sum to zero. So I can diagonalize this matrix. Let's say this I'm doing for G equal to SUN, which will be the case that we will consider. So when I am on the moduli space of this theory is parameterized by the waves of these complex scalars, and I need to satisfy that V is zero, this matrix can be diagonalized. So generically, this type of waves have the effect of breaking the gauge group down to U1 to the n-1 times some residual symmetry, which is the vial of SUN. So the moduli space, in this case, is just Cn-1 divided by these redundancies that I still have, which is the vial symmetry, which is for SUN is just the symmetric group of order n-1. So classically, we expect that we might have some singularities when some of these waves, some of these coefficient A1 to AN collide, and so we have a degenerate vacuum that is not completely Higgsing the gauge group to U1s. So in this case, we would expect singularities because we will have extra massless mode. But so classically, we expect singularities due to massless modes when waves are degenerates. But this is only really a classical picture, and the goal for the remaining lectures will be really to understand the moduli space of vacua of, well, we will focus on the SU2 case, which is interesting enough to understand really what happened at the quantum level to this moduli space. So we'll, of course, come back to this discussion, but before I would like to complete the construction of n equal to Lagrangians. So, so far we only discussed a Lagrangian for the vector multiplet, but we also have hypermultiplets. And in this case, we constructed in the representation theory this multiplet starting from helicity state -1/2, and we constructed this hypermultiplet and its CCPT conjugate. And now this guy can be regarded as two n equal 1 chiral multiplets. So we want to combine these two n equal to chiral multiplets, which I will call, so small q will be for me the scalar into an n equal 1 chiral multiplet, which we can call capital Q. No. And then we will have another n equal 1 chiral multiplet, which I call Q tilde, with scalar Q tilde and fermion psi Q tilde. So in terms of n equal 1 multiplet, this will be an n equal 1 multiplet, and this will be another n equal 1 chiral multiplet. And I'm arranging them in this way because I want to highlight the action of the SU2R symmetry. And if you remember our discussion now, it was the scalars that are doublets under the SU2R symmetry. So now we can wonder, how do we write Lagrangian, which includes n equal 2 hypermultiplets? Well, I can use again the n equal 1 language. And interestingly, now you may think that n equal 2 symmetry is not, supersymmetry is not restricting us too much, because we can insert, in principle, superpotential. So in principle, we can do many things. So let's write down first the thing that we are expecting. So this will be the part of the n equal to Lagrangian that we need to describe matter. So sorry, bar. I will write first of all the kinetic terms for the two multiplets. So notice now the SU2R is forcing me to choose the same normalization in front of the two kinetic terms, because I want the two scalars to transform with the same normalization. So the two scalars, they are rotated by SU2R. Now I have here VR, because now I can choose a rep under gauge of the Q and Q tilde n equal 1 multiplets. And now it comes the interactions. Basically, so for sure, I can write down a term which involves the chirals and so the three chirals field that I have. So phi is the chiral multiplet that sits in the vector multiplet, and Q and Q tilde are the two n equal 1 multiplet that sit into the hypermultiplet. And basically this interaction, the way I am contracting indices, preserves SU2R and also U1R. And it is interesting that if I try to make more interactions, basically I can only make SU2R invariant interactions, but they will be non-renormalizable. So if all the cubic interactions, okay, we are talking about superpotential, so, and you're using chiral multiplets. So everything with power less than 3, apart from this combination that I wrote down, phi Q Q tilde, is going to be breaking SU2R. In principle, you can write more interaction terms, but they will be non-renormalizable. So you can write more general interacting n equal to Lagrangians, but they will not be renormalizable. Of course, you can add a mass. You can add a term which is m QQ tilde. This is going to be, okay, so we will preserve SU2R and will be obviously normalizable. So this is the discussion at the level of the classical Lagrangian. So we wrote down something that preserves SU2R times U1R, but this U1R is going to be anomalous. And you see, in n equal 1, we could find an assignment of charges under U1R so that U1R is not anomalous. But here we don't have freedom to do so because we have to assign the U1R charges to be consistent with SU2R symmetry. And so we fail. In fact, remember, we have to say that the gaugino and the fermion in the chiral multiplet, they both have R charge 1. So if we calculate the usual triangle diagrams for U1R and to gauge currents, and then you find sum over the fermions, the R charge times T of the representation. So now see how things are going. So now we have the gaugino, which has R charge 1, and it lives in the adjoint. So this is the gaugino. And then we have, for the other fermion, it's the same because it has R charge 1, it is also living in the adjoint. So this gives 2 and C, and this is non-zero, obviously. So there is an anomaly which shifts the theta angle by 4 and C. So this means that U1R, it's broken by 2Z, 4, and C. In fact, since we saw that the scalar has R charge 2, when we are on the moduli space, so when we are in a vacuum, it's gonna further break our symmetry. So this is because, so remember that we have a coupling, which we just wrote is Q phi Q tilde. So this implies that the R charge of Q and the R charge of Q tilde is 0. Okay, so it means that the R charge of the fermion sitting into the hypermultiplet, it's -1. So when I also consider matter, U1R is broken to Z, 4 and C minus 2 and F. So the effect of U1R rotation shifts the angle by the theta angle by 4 and C minus 2 and F. So that's the effect of the anomaly of all the fermions that we have. And as I was saying, if you are sitting in a vacuum, VEV further breaks Z4 and C, because when you give a VEV, there is also, you are turning on something with R charge 2. So for example, you may have that for SU2, you have that U1R, it's broken to Z8, and by the VEV is further broken to Z4. And this is something that we will need later. So My time is a bit, I'm a bit late. Let me see what I can say. Yeah. And maybe I will start discussing the effective n equal to theories, but then I'm afraid we will have to break and resume tomorrow. So effective n equal to theories. So this is basically talking about the non-renormalizable sigma models. So we discussed this briefly in the n equal 1 case. For n equal 1 theory, we said that if you have a theory that at low energy is, well, you need to have matter, first of all. You have a gauge matter theories, and you find yourself at low energy with some effective action where you still have gauge fields, then your effective action in general may have a form where you generalize the typical form of an n equal 1 Lagrangian by replacing your gauge coupling to a generalized gauge coupling. So A and B are gauge indices, remember, and this object FAB, which is a function of, which is a function, holomorphic function of the scalars, transform in the adjoint times adjoint, so it has two gauge indices. And this is the generalized gauge coupling. And at the same time, we said that when you undergo such a process of going to low energy and Wilsonian renormalization, also the kinetic term, the gauge invariant kinetic term, can be replaced by a more general function, which is this Kähler potential. But this time is a function of the e to the GV acting on phi bar time n phi. So this was the observation we had for n equal 1, but in the n equal 2 case, because precisely of all the restrictions that is set by the SU2R symmetry that rotates the two supercharges and so fixes all the normalization. So in the n equal 2 case, what happens is that this generalized coupling, FAB, and the Kähler potential, they are not independent, but can be written in terms of a single holomorphic function. Which is called the prepotential. Phi, which is a holomorphic function of the chiral fields. In this case, if I'm doing pure n equal to supereminence, it's just a holomorphic function of phi. So more precisely, the generalized coupling is simply going to be the second derivative of this holomorphic prepotential respect to phi and phi bar. Remember now that phi, it's the chiral superfield in n equal to vector multiplet, so A is an adjoint index. And then the Kähler potential, it's minus 1 over 32 phi bar A F A minus F bar A Fa, where Fa is just the first derivative of f respect to phi. So in a very, we can write everything in terms of this holomorphic function, the prepotential, because the low energy effective action preserving n equal to is now completely determined by the generalized coupling and the scalar potential, which are just given in terms of a single function. So the goal, if we want to claim that you solve the low energy, you understand the dynamics of a low energy and n equal to theory, it means that basically you need to determine a single holomorphic function, which is the prepotential. Because if you know the superpotential, then you can, sorry, the prepotential, then you can write down the effective action. So there are, you cannot do anything else. That's it, if you can fix this function. And this is what Cyber-Witten managed to do. And so the plan is gonna go to their argument in the next lectures. So let me only mention that, of course, if you, just to have an handle on what is this, this function, if you choose the prepotential equal to 1/2 tau trace phi square, basically you go back to the classic, the original UV, meaning that before we did this process to go to low energy effective action, we go back to the n equal to renormalizable Lagrangian that we have in the UV. So my time is running up. So before really moving to Cyber-Witten, I need to discuss quickly the renormalization properties of n equal to theory. And then we will move on to the work of Cyber-Witten. Okay, so